Okay, in this video, we are going to look at certain laws, Savart law and Ampere's law. Okay, these are the two persons that made contribution in calculating the magnetic field, around a current carrying conductor. Now, Savart law is an equation that gives the magnetic field produced due to a current carrying segment. Okay. This segment is taken as a vector quantity known as a current element ideal. The law states that the magnetic field created by current I is directly proportional to the product of the current, length of the conductor, and sine of the angle between the conductor and the direction of magnetic induction B, and inversely proportional to the square of the distance from the conductor to the point P. Now that is it here. So according to that, we have this. That's the B is equal to mu naught over 4 pi is the constant there. We have IDL. I there is current. DL there is or remember the IDL is the current length. That's the current element. Okay. Then sine theta is of course the angle. Then while R squared, R there has to do with the distance. Okay, the distance from the point of the field to the current. Okay, so if the B is equal to mu naught over 4 pi IDL sine theta all over R squared, to find B now means we integrate both sides. Okay, so making B subject of formula, we integrate both sides. We have mu naught over 4 pi integral of IDL sine theta all over R squared. Now remember that mu naught is the permittivity of free space and is equal to 4 pi times 10 to the power minus 7. Now you may want to understand this diagram, but if we say this is the part of the current, that's the part of the current. Okay, now this is a current element. Just sometimes when you have something large, in order to understand the large thing, or in order to get to break it down, you pick just an element, a small part of it, which is what we call the L. The L is just the small part we pick to work with. So that part, if we want to find the electric field at point P, there's a distance between from that point to point B. That's what we call R. And the L here is a fraction of L. Then D here is the perpendicular distance. Okay. Now, but in this video, I'm not going to bug you with all the provings and all that. So we'll just go straight to the point. Now this formula has led to a lot of formulas. Like here, we see magnetic field due to a flat circular coil carrying current. Now, if you have a flat circular coil, just like this diagram here, this is a coil, a circular coil, and the coil is carrying current. Then the magnetic field along the axis of the coil B is mu naught I A squared all over 2 into A squared plus X squared raised to power 3 over 2. Okay. Now, but if X is much greater than A, look at the position of X. Look at A here. If X is much greater than A such that it is neglected, that means you can neglect A. In that case, that denominator here, this denominator here is going to look like this: 2x squared raised to power 3 over 2. Okay, making that 2 can cancel 2, so I'm left with just 2s cubed. That's why we have this. So if you're asked to find the electric field, at a point along the axis of the coil, where x is much greater than A, then we are going to have mu naught I A squared all over 2s cubed. Please notice the formula. But if you're asked to find the electric field at the center of the coil here means that your x is equal to 0. So in that case, the whole of this formula is reduced to this, which is B equal to mu naught N I all over 2A. Please, let's not forget that. Now, that formula, the whole of Savart formula, is reduced to this. If we are asked to calculate the magnetic field due to a solenoid, okay, it's reduced to m mu naught Ni all over L. Now, what is a solenoid? A solenoid, this is a solenoid. I'm sure you should have seen this. Is when you wound a wire, to form a coil like this. And this diagram here shows the magnetic field inside the solenoid. So according to Savart law, like I said, I'm not going to bog us with how we got to this. We should just know that the magnetic field due to a solenoid is B equal to mu naught Ni all over L. Okay, so that leads us to, this is a continuation of that. There is a broader formula of magnetic field along a solenoid, which is B equal to mu naught Ni all over 2L into cos theta 1 minus cos theta 2, depending on the position. Okay, now but if theta 1 is 0 degrees and theta 2 is 180 degrees, then that's where we have that B is equal to mu naught Ni all over L. Of course, the 2 will be cancelled out. That's because cos theta 1, cos 0 is 1, then minus cos 180. Cos 180 is minus 1. So you have 1 minus 1, which is equal to 2. So this 2 cancels out this 2 here. Okay, so you have B equal to mu naught Ni all over L, which you can also write as mu naught small n L. This small n is equal to number of turns per unit length. Okay, you should note that. So we can either use this formula or we use this formula. Okay, now magnetic field due to a toroid. What is a toroid? A toroid is a solenoid that has been curved to become a circle, like as you see in this diagram. So if it is a toroid, the magnetic field is mu naught Ni all over 2 pi r. Okay, so let's see questions here. This one says a straight current carrying wire carries an electric current of 200 amperes. So current is 200 amperes. What will be the magnetic field due to the current at a point 2 meters away from the wire? What will be the magnetic field due to this current at a point 2 meters away from the wire? Now, a straight wire carrying current experiences a magnetic field B equal to mu naught I all over 2 pi r. That's the formula for the magnetic field at a point by a straight wire, sorry. So your mu naught here is 4 pi times 10 to the power minus 7. Now multiply by current. What is current? Current is 200 amperes divided by 2 pi r. That means 2 pi multiplied by the r here is the distance. At what distance? 2 meters. So if we calculate that, we are going to get 2 times 10 to the power minus 5 Tesla. Okay, that is the value. Earlier on, before now, I didn't mention that, but from this question, you can see that the magnetic field due to a straight wire carrying current at a point is B equal to mu naught I all over 2 pi r. Okay, so here it says a circular coil of radius 5 times 10 to the power minus 2 meters with 40 turns is carrying a current of 0.25 amperes. Determine the magnitude of the circular coil at its center. So this is the formula we have. The magnetic field at the center of a circular coil. This is a circular coil we are dealing with. Okay, is mu naught Ni all over 2a. A is the radius of the coil. So if we substitute value, we are going to have 4 pi times 10 to the power minus 7 multiplied by n is the number of turns, which is 40, multiplied by I, which is current at 0.25, then divided by 2a, 2 times the radius. Radius is 5 times 10 to the power minus 2. Okay, now if we use our calculator to get that done, we're going to have Okay, let's do that quickly. We have 4 pi times 10 to the power minus 7 and multiply by 40, then multiply by 0.25, and the denominator we have 2 times 5 times 10 to the power minus 2. Okay, that's giving us 1.26. We have 1.26 times 10 to the power minus 4 Tesla. Okay, that's the value we have. So you see, you just know the formula and you're okay. Now look at this one. Consider a circular conductor again. We radius 2 meters and 8 amperes current flowing through it. Determine the magnetic field intensity at the center of the circular coil. The same question. So we use this formula mu naught Ni all over 2a. Your mu naught, like we have, is 4 pi times 10 to the power minus 7. Okay, multiplied by Ni. N is number of turns. In this case, we are not given a number of turns, so we'll assume it to be 1. So there is no turn here. Then multiply by I. What is I? I is the current, that means 8 amperes, divided by 2a, 2 times the radius, that means 2 times 2. So in that case, we are going to have this is multiplied by 1 exponential minus 7 multiplied by 8, now divided by 4 as the denominator. So that will give us 2.5 times 10 raised to the power minus 7 Tesla. Okay. So that leads us to another question. In this case, it's a solenoid. Evaluate the magnetic flux density in a solenoid with 50 tons per centimeter. Okay, the 50 tons per centimeter, that's the number of tons per unit length, carrying a current of what now? 6.2 amperes. So we're going to use this formula here. We have 4 pi times 10 to the power minus 7 multiplied by number of tons per unit length here is 50. Actually, it should be 50 over 0.01. That's converting centimeter here to meters. So 0.01. Okay. Then multiply by I, the current is 6.2 amperes. Now, if we do that, we are going to have 4 pi times exponential minus 7 multiplied by 50 times 6.2 divided by 0.01 is going to give us 0.039. So we have 0.039 here, Tesla. Okay, this is beautiful. Now let's see another question here. This is also for a solenoid. A solenoid is 1 meter long and 3 times 10 to the power minus 2 meters mean diameter. Okay, it has 5 layers of windings. We take note of that, and of 850 tons each, and carries a current of 5 amperes. So the A part says calculate the magnetic flux density B at the center. Calculate the magnetic flux density B at the center. Then the B part says we should calculate the magnetic flux for a cross section of the solenoid at the center. Okay, that is not a problem. Now a solenoid is one. Let's see here. This is the formula we are going to use here. Okay, we have B to be equal to mu naught Ni all over L, which is mu naught N all over L. So, but here we are given a number of tons, we are given the length, so we'll rather use this. Now your mu naught is 4 pi times 10 to the power minus 7 multiply by n. N is the number of turns, and we have 850 turns, but we have 5 layers. So because of the 5 layers, we are multiplying by 5, then by 850. Then the current is 5 amperes, so we say multiply by 5 again. Now divided by L, the length is 1 meters. So let's see this. Then multiply by 5 times 850 times 5, then divided by 1. So here we're going to get 0. The answer here is 0.027. Okay, let's have it like this. 0.027 Tesla. Now that's for A, that's the magnetic flux density. Now the B part says we should find the magnetic flux for a cross section of a solenoid at the center. Okay, the magnetic flux. Now what is the relationship between magnetic flux and magnetic flux density? It's important for you to know that magnetic flux is equal to magnetic flux density multiplied by area. Okay, so your B, we got it to be 0.027. Now multiply by area. Area is given here. We are given the diameter. We know that area should be pi d squared over 4 since we are given diameter. So this should be times 3.14, which is pi. Then times d squared, which is 3 times 10 to the power minus 2 all squared. Then finally divided by 4. Okay, so if we use our calculator, we'll get 0.027 multiplied by 3.14 multiplied by 3 times 10 to the power minus 2 squared, then all divided by 4. Okay, we are going to get that magnetic flux is 1.91 times 10 to the power minus 5. The unit is actually Tesla meter square. Okay, Tesla meter square. So you should know that, or just simply Weber, WB, Weber. Okay. Now this leads us to Ampere's law. I'm not going to be saying much here because Ampere's law and Savart law in most of the cases arrive at similar conclusion in determining the magnetic field, at a point. But let's see Ampere's law. It says the magnetic field created by an electric current is proportional to the size of the electric current with a constant of proportionality equal to the permittivity of free space. That's exactly what we have here. Integral of B dl is equal to mu naught I. Now, Ampere's law gives us the same value. Okay, let's see, for example, if I want to find, according to Ampere's law, if I want to find the magnetic field due to, what is it called now? A conductor, a straight wire carrying current. So we already have that B dl is equal to mu naught I. Now, the magnetic field around the straight wire carrying current is a circle. So B, your dl, that means your element here is going to be 2 pi r. That's the circumference of that circle, which is equal to mu naught I. Okay, so you see that your B now will be mu naught I all over 2 pi r, which is exactly the formula I gave you for the magnetic field at a point due to a straight wire carrying current. So that's the same thing. We will get to the same formula that by your Savart law, arrived at, but using a different method. So that is how we end this class here. Thank you very much.